Let us just wait for another 2 minutes before starting
Battery is discharging.
to see if somebody else is joining the call, joining the class today. Okay, so let us begin today's session. I hope that the screen is visible to everybody and that I am audible.
Yes, sir.
Okay, so I think my video is coming due to some reason. Just let me retry once again. Yeah. So I'm still audible, right?
Yes, sir.
Okay. Yeah, and the screen is visible, right?
Yes, sir.
Okay. Okay. So without further delay, let us begin today's session. So I welcome all of you to the 10th live session of the course Fundamentals of Manufacturing Processes being offered by Dr. D.K. Dwivedi of IIT Roorkee. As in for myself, I am Abhik Debe, PhD scholar in the Department of Mechanical Engineering at IIT Bangalore. And today I shall be um, discussing on the problems related to some concepts in the continuation of the grinding operation and to the introduction of the joining operation. Okay, so in the previous class itself, we discussed quite a few problems related to the grinding. So we will be continuing some of the concepts, some of the remaining concepts in today's class, and then we will be moving on to the problems related to joining. Okay, so yeah. The favorable impact of high temperature during the grinding on the workpiece is which of these: oxidation, the burning of the surface, the residual compressive stress, or soft spots? So, does anybody have an answer to this? Yes. Any idea? Okay, so what happens during grinding is that because of the rubbing action, the plowing action, as well as the main cutting action of the abrasives on the workpiece, there is a there is either a plastic deformation or erosion, or that is, or cutting of the material from the workpiece surface. As a result, due to this cutting operation, the heat that is generated is being carried away partly by the small chips and partly by the wheel, and then a lot of temperature is actually generated on the workpiece. Okay, since in contrast to any other cutting operation, the fraction of the chip is very less. Okay, the amount of chips formed is very less, so the amount of heat that will be carried away by the chip is also very less. In that case, the maximum amount of heat will be generated in the a large amount of heat in this case will be generated in the workpiece, which results in a very high temperature on the workpiece surface, and so to some extent to the bulk of the workpiece also, if the workpiece is very large. Otherwise, the entire workpiece will become hot. Now what happens is during this high due to this high temperature, the surface of the workpiece, the surface material of the workpiece can interact with the nitrites and the oxides, sorry, nitrogen and oxygen present in the atmosphere, resulting in the formation of their oxides or nitrites. So this oxidation, whatever this oxidation happens, this oxidation is responsible for the decolorization. That is, suppose we are any material we are taking, any particular metal, and it gets oxidized, then then that oxide will have different uh, composition and different properties with respect to the bulk material, and the color will also be different, so we can visually differentiate it due to the decolorization that the oxides are present. So this results in decolorization of the surface, workpiece surface. Okay, so this is not a favorable impact. Okay, so this is a like you can say a negative impact of the high temperature. Now burning of the surface. See, burning of the surface is also it is not a what we can say, it is not a positive impact of the high temperature during grinding. But the residual compressive stresses, what happens is that when there is high temperature during this grinding, so the workpiece surface will expand due to this high temperature. Okay, the only the surface, since we are only manufacturing sorry, we are only machining the surface, so the surface will expand a lot because of this high temperature. Now when it cools down, the dimensions has to come back to the dimension of the bulk material, but the bulk material is not heated as such. So there, due to this difference in the temperature, there will be you know that the uppermost layer of the workpiece will be forced to contract to the dimension of the bulk material, of the bulk surface, sorry, of the bulk workpiece substance. Due to this, what I am meaning to say is, suppose this is the workpiece that we are grinding, and this is the significantly heat affected region, that is the temperature is significantly high. Due to the high temperature, this gets expanded like this region gets expanded, whereas the bottom region does not expand as such because the temperature is not that high. Okay, so when the material will contract, that is when the material when the temperature drops. Okay, so this extended regions, or the regions that have formed because of the high temperature, will try to regain the dimension of this bulk material. Due to this, there will be a compression developed here on the uppermost layer of the surface. So compression develops on the uppermost layer of the surface, layer of workpiece, sorry. So what is this? Suppose this is the workpiece now. So this region, this entire region will be under compressive stresses. Compressive stresses like this. Compressive stresses. Now see, if this substance is now subjected to a tensile loading. Okay, compressive. So this workpiece is now subjected to a tensile stress, say tensile stress of T. Okay, so if the yield strength of the material is suppose if the yield strength of the material is say suppose T naught, then at the value of the tensile stress equal to T naught, the material would have started deforming without the presence of this compressive residual stress. Now, due to the presence of this compressive residual stress, whose amount is say C, the material will start deforming when the tensile stress becomes equal to will start deforming at tensile stress value of T naught, that is yield strength, minus plus C plus the compressive stress. Okay, that is compressive stress is like a resistance, right? It will try to by tensile stress we are trying to pull the material apart, but the compressive stress is like trying to push the material together. Okay, so this T naught plus at T naught plus C, the material will start to deform. So as we can say that the yield strength or the strength of the material increases under the tensile loading condition. That is why this compressive stress is a benefiting factor. The residual compressive stress is a benefiting factor for the material under working conditions. Okay, so that is why the bene uh, main favorable impact of high temperature during grinding is the generation of residual compressive stress. Okay, so the correct option is option number C. So is it clear to everybody?
Yes, sir.
Okay, okay, then let us move on to the next problem. So to prevent the blunting of the cutting tool, the tool material should have which of these properties? High toughness, high hot hardness, chemical inertness with the workpiece, and higher coefficient of friction. Can anybody give me the answer to this?
Sir, option B.
Yes, option B. Yeah. So the blunting of the cutting tool is mostly because um, at high temperature generated during in the cutting tool during the machining operation, there will be plastic deformation, and also there is a chance that the material at the edge of the cutting gets deformed because of that. So there is a due to that high temperature to retain the shape of the cutting tool at that high temperature, the cutting tool material should have high hot hardness. Okay, so the correct option is option number B. Now, coming to the next question, in cemented carbide tools operating on steels, the titanium carbide and tantalum carbide are added to increase the toughness, to increase the corrosion resistance, to prevent the oxidation of tool, or to prevent the wear due to diffusion of carbon into steel. What about this? So what is cemented? What is the basic composition of cemented carbide? You know. Anybody? Okay. So what happens is, see, in cemented carbide tools, we generally have this cobalt with tungsten carbide for the as cemented carbide tools. Okay. Now what happens is that suppose we are trying to operate on steels. Now steels contain iron, okay, which has high affinity for carbon. So this the when we operate on steels using cemented carbide tools at that high temperature, at a high temperature during the cutting operation, during the machining operation, the iron will tend, the carbon will tend to diffuse to the steel because the iron in the steel has a high affinity for the carbon. Okay, so this results in the loss of carbon from the tungsten carbide. This is tungsten carbide, right? WC. So from the tungsten carbide, there is a loss of carbon. So the gradually the strength of the tools, cemented carbide tools, will decrease. Okay, or the hardness of the cemented carbide tools will decrease. To prevent this, mm, uh, carbon diffuses to steel. To prevent this, this titanium carbide and tantalum carbide are added because these compounds, titanium carbide and tantalum carbide, in contrast to tungsten carbide, these have very high affinity for keeping the carbon with themselves. So the addition of these will prevent the diffusion of these carbon atoms to the steel. As a result, the strength and hardness of cemented carbide tools can be maintained during machining of steel. So this is essentially only because for the machining of steels. If some other non-ferrous alloys are being machined, then in for the machining of those, this titanium carbide and tantalum carbide did not be added because in non-ferrous alloys the carbon diffusion will not be a problem because iron, if not present or present in very less quantities, then it won't be able to that is its affinity for carbon will not be significant enough to cause the diffusion to a significant extent. That is why, so this is not required for non-ferrous alloys, for the machining of non-ferrous alloys, but for the machining of steels this is very much required. Okay, so the correct option will be option number D. Okay.
So,
Yes.
even if the carbon diffuse into the tool, it's actually good, isn't it? So if the carbon content is increasing, then the hardness of the tool will be increasing, isn't it?
No, the carbon will diffuse from the tool to the workpiece. The tool is a cemented carbide of the tool is of cemented carbide. So the tool is containing carbon. Okay, and the steel is will be containing a large amount of iron. So because of the affinity of iron with carbon, the carbon will diffuse from the tool to the workpiece. So the tool will actually lose carbon, and as a result its hardness will decrease.
Okay, sir.
Yeah. So is it clear to everybody?
Yes, sir.
Okay. Okay. So then let us move on to the next problem. So friability. So friability refers to which of these?
Sir, it is it the option D?
No, not really. The abrasives getting attached with a workpiece at high temperature is not friability. Actually, friability is the exposure of the new cutting edges by the breaking of abrasives. So what happens is that when the abrasives are machining the workpiece, it might so happen that because the abrasives are mostly of hard and brittle materials, right? So these abrasives will have the tendency to break. Okay, so if an abrasive was like this initially, abrasive 1 on the, and it is machining this workpiece. Just sorry. Okay, this is the workpiece it is machining. Now in the second stage, because of the breaking, the abrasive becomes something like this. Say it breaks like this. Now this will be the cutting edge. From here, if it breaks like this, then a new abrasive will be coming in for operation. So this cutting edge, this might have become blunt or something, and this breaks, and a new cutting edge is exposed for the machining, and this will be sharp again. This will be sharp. Okay, so this phenomenon, mm, okay, abrasive 1 breaks. Okay, to generate this abrasive 2. Now this phenomenon, that a new cutting edge is now exposed to the workpiece because of the breaking. This is not true for, the single point cutting tool or what we were discussing previously, because those were of much larger sizes. So if they break, okay, their broken portions will not be adapted enough for a for the cutting operation once again, unless we tried unless we process them for maintaining the angles, the tool angles, particularly. But uh, for these abrasives, for very minor, because they are of such minute sizes, the breaking of the one abrasive will result in the exposure of a new cutting edge. Okay, so this new cutting edge will have a better tendency for machining with respect to the previous cutting edge, say, which was becoming blunt. Okay, so this phenomenon is referred to as friability. Okay, so the correct option is option number B. So is it clear to everybody? Okay, so let us go to the next problem. So the break-in period in the wear of the grinding wheel refers to which of these? Any idea? The wearing of the grinding wheel is like a uh, mm, it has three different stages. So the breaking period is a one particular stage of the grinding. During that, which of these happens? Yes, any answer for this? Okay, so see, the wear of the grinding wheel, if we plot it with the MRR or the uh, material removed, the rate of the material removed, then we will find that the wear of the grinding wheel occurs in three stages like this. First is this break-in period. Okay, now this is steady wear. Okay, the steady wear is due to the attrition. Can anybody tell me what is attrition? Can anybody tell me what is attrition?
So it reduces the strength.
Strength of what?
Strength of material.
Which material? Like the workpiece material or which material?
Workpiece.
Okay. And this is the fracture. Okay. So attrition is not essentially the reduction in the strength, but it is referred to the gradual wearing of the abrasives. Okay, so we start off with sharp abrasives, and the abrasives are gradually becoming blunt. Okay, because of the cutting action, and if we are like if they are not breaking by themselves, then new cutting edges will not be will not be exposed. So we are not considering this previous phenomenon. We are just considering that they are gradually wearing out of the abrasives. This gradual wearing out of the abrasives is called the attrition. That is, the sharpness of the abrasives is decreasing. Okay, and then there is fracture. So in the break-in period, there is the wear rate is decreasing. See, this is the wear rate, the slope of which is decreasing. So the wear rate decreases. Wear rate decreases. This is almost a constant wear rate. This is a constant wear rate, and this is wear rate increases. So wear rate here increases till there is fracture. So break-in period refers to the time when the wear rate decreases. So break-in period refers to the time when wear rate of grinding wheel decreases. Correct option will be B. Okay. So is it clear to you? Or if there is any doubt, you can ask.
Yes, sir, clear.
Okay. Now coming to the next problem, with the increasing wheel speed, the grinding ratio and the surface roughness increases or decreases. Think about this. These were discussed in the theory class, so I think so you should have been able to answer this. With the increase in the wheel speed, what happens?
Sir, I think option B.
Option B. So the grinding ratio increases and the surface roughness decreases. Yes. So why is it? What is grinding ratio? Wheel wear, right? By MRR. Rate of wheel wear. Sorry, I have written the opposite. Grinding ratio is the material removed from the workpiece. Rate of wheel wear. Okay. So if the wheel speed increases, then at that high speed, what will happen? Then the per unit time, the material removed from the workpiece will increase or decrease if the wheel speed increases. If the wheel was removing the material, okay, wheel was removing the material, and now uh, mm, uh, the speed of the wheel is increasing, then whatever material was initially removed in 1 minute, now in 1 minute the material removed will increase or decrease? Okay, tell me this. When suppose the wheel was initially moving at 4000 rpm, and due to this rotation of the wheel, say in 1 minute, say 50,000 abrasives were come into contact with the workpiece. Okay, from this region, whatever this is rotating, and now the speed is increased to 8000 rpm. So in 1 minute, the number of abrasives that come in contact with the workpiece will be more than 50,000 or less than 50,000, or it will be equal to 50,000. Yeah, anybody, please. Like, this is a very basic question. I am audible to everybody, right?
Yes, sir.
But why I am not getting any answer? Like, this is very common, right? These are the abrasives which are in contact with the workpiece. Now, at any particular speed, say 4000 rpm, say 5 abrasives were coming in contact. Now if we increase the speed, the number of rotations will increase, right? So more or less abrasives will come in contact. That is, the number of abrasives coming in contact will be more or less.
It will be more.
Huh, sorry?
More abrasive will be coming contact.
Yes, more abrasive will be coming in contact, because one rotation completed, then this abrasive will again come from this side once again. Okay, so more abrasive will come in contact with the workpiece. So what does more abrasive mean? More abrasives means that more material per unit time or per minute, whatever you take, the amount of material removed will be more. Okay, so the material removal rate from the workpiece increases. Okay, so this value increases. This value increases as wheel speed increases, material removed from workpiece per unit time increases. So grinding ratio increases. Okay. Now what about surface finish?
Surface finish will be increasing.
Will be,
Increasing. Finish.
yeah, surface finish will increase, and what about surface roughness will decrease?
Yes, sir.
Why so? Why do you think? It is the correct answer, but why do you think so?
So finishing means the roughness will be reduced. The more material will be uniformly removed, and
Mm, uh, you can think it in this
Sir,
direction.
if surface finish increases, then surface roughness decreases because these both are inversely proportional to each other.
Yeah, but I am asking why any of these increase or decrease with the wheel speed. See, when uh, when the wheel speed increases, the time of contact between one particular abrasive, the time of contact, suppose when the speed was 4000 rpm, the one abrasive was in contact with the workpiece for some, you can say, suppose 10 millisecond. Okay, now as the wheel speed is increased, this abrasive will now be in contact with the workpiece for much lesser time. Okay, 5 milliseconds say. So in this 5 millisecond time, the although the number of abrasives in contact is increasing, but the material removed by one single abrasive will be less, okay, as compared to this, because it will be coming in contact with the workpiece for a very less amount of time. Okay, in that time a lesser amount of material will be removed. So this mm, you know, the this uh, if the material was initially removed by the at the slow rpm, then the surface roughness will be of the order of this indentation, okay, this penetration. But now the surface roughness will be of the order of this penetration, which is much smaller. As a result, the surface roughness will be decreasing and the surface finish will increase when the wheel speed increases. Is it clear?
Yes, sir.
See, with increasing wheel speed, each abrasive gets lesser time to interact with the workpiece. So surface roughness decreases. Okay. Okay. So you can consider this diagram for your consideration, and there is a very good chart for this. So with the wheel speed in this direction, and this is the grinding ratio and surface roughness. Okay. So the with the increasing wheel speed, the grinding ratio will come down. The grinding ratio, sorry, the grinding ratio will increase like this. This is the grinding ratio, and the surface roughness will similarly decrease like this. This is surface roughness. Okay. So the correct option will be option number B. And I would also like to mention here that at very high wheel speed, the grinding ratio will again start decreasing. Why? Because at very high wheel speed, the temperature will be extremely high. In that, for that very high temperature, uh, in that very high temperature, the wheel wear will also significantly rise. As a result, the grinding ratio will start gradually decreasing. So it will, but for the general operations with the increasing wheel speed, the grinding ratio usually increases. Okay, so should we move to the next problem?
Yes.
Yes, sir.
Okay. So for dry grinding on large area, which of these type of abrasive is to be used? Soft or hard, and coarse or fine? So we have to take individually for dry grinding and for large area, and we have to see which is to be used. So any idea about this? Yeah. So see, in dry grinding. So what is the difference between dry and wet grinding?
So there will be coolant or anything.
There will be.
Coolant.
Sorry, I could not get you. There will be. What did you say?
So coolant
Yeah, yeah,
for.
yeah. Coolant. Yeah, that is cutting fluid will be there, and in one there will be no cutting fluid. See, so in dry grinding, no coolant. Okay, so heat removal becomes difficult. Correct. So what will we do? So if the grade is hard, hard grade implies abrasives are not removed from wheel, not removed from wheel. Soft grade means abrasives are removed from wheel. Okay, now our main aim that heat removal, since it is becoming difficult in dry grinding, we have to increase the heat removal capacity. So if the abrasives are removed from the wheel, if abrasives are not removed from the wheel, in that case the heat will be removed easily, or if the abrasives are removed away from the wheel, in that case the heat will be removed easily.
So for the soft graining abrasives will be not removed, isn't it?
Sorry.
For the soft grinding grade, the abrasive will be not easily removed.
No, I am asking that in soft grade the abrasives will be removed. In hard grade, the abrasives will not be removed from the wheel. Okay, right?
Yes, sir.
Yeah. So if the abrasives are removed away from the wheel, then will then the heat removal be easier, or if the abrasives are not removed from the wheel, then the heat removal will be easier? Mind you that the abrasives will carry away the heat. If they are removed, then abrasives will take away heat like chips. Right, so this abrasives taking away heat will be possible if the abrasives are removed or abrasives are not removed.
So the abrasives are removed, then the heat transfer will be more.
Yes, so abrasives are the removed, then the abrasives will take away the heat. In that case, the heat removal becomes easier. So now, can you tell me, thus for dry grinding, we will require soft grade or hard grade?
Soft grade.
Yes. So see, it is very intuitive. Once you start knowing how to think about like this, you will be able to answer any question. So see, heat removal becomes difficult. So we will prefer to mm, prefer that abrasives take away heat. So soft grade. Okay. Now coming to the large area. What does large area mean? Large area, that see, if the grinding wheel
Battery is fully charged.
now large area means a large area is being machined and small area is being machined, is that means when for large area more abrasives will be in these abrasives will be contact with this large area. Now and for a small area, lesser number of abrasives will be in contact with the workpiece. Okay, so the cutting force by this is the area. So pressure the pressure on the grains, pressure on the abrasives will be more in which of these? If a1 is great, it is a1 is greater than a2, right? So fc by a1 will be less than fc by a2, right? That is, in this case the pressure is less than this pressure. Here the pressure is more distributed on a larger number of grains. Here the pressure is distributed, due to cutting force, the pressure is distributed on a relatively smaller number of grains. So since the pressure is more on these grains, this on these two grains or whatever grain is coming in contact in this cutting operation, in this grinding operation, the pressure will be more. Due to so to take care of this high pressure, okay, also so under this high pressure the abrasives will tend to become blunt easily. So we will prefer that the abrasives, these blunt abrasives, get removed easily. Okay, so for this high pressure, to withstand this high pressure, the abrasives will become blunt, and this abrasives, we will have the tendency that the abrasive should be removed easily, and hence we will also prefer soft grade. Okay, this is for that is for uh, mm, sorry, just give me a minute. Yeah, I got confused. Sorry about that. See, the initial idea is the same that we have discussed. So for large area, this is the greater number of abrasives are coming in contact. For small area, lesser number of abrasives are coming in contact. So here the pressure is more, P2, and this is P1. So P1 is less than P2. Okay. Now for the coarse grade, what happens is that the abrasives are widely spaced like this. Okay, so this lesser pressure, this pressure value which is less, this can be which to the like widely distributed abrasives can withstand this lesser pressure value P1. Okay, but if this uh, widely spread abrasives are subjected to a pressure P2, then they might fail. So we will be needing more abrasives to withstand this pressure P2. To withstand the pressure P2, we will be needing more abrasives, because since P2 since P2 is higher, since P2 is higher, we need more abrasives to withstand the pressure. So we will be needing a fine spacing of the abrasives like this for withstanding a higher value of pressure. Okay, this diagram is a bit misleading, so I will correct this. Suppose suppose we are taking equal spacing for now, then yeah, this is fine. So with equal spacing, irrespective of it is coarse or fine, suppose this is the spacing shown here, then for a large area, more abrasives will come in contact with the area, so the pressure will be less. For a smaller area, the lesser abrasives will come in contact, so the pressure will be more. To withstand this high pressure, we will need a denser settlement of the abrasives, so fine grits are used. But for lesser pressure, that is P1 value, we will be needing a wider distribution. That is, if the abrasives are coarsely distributed, then also the pressure P1 can be withstood by the abrasives. That is why we will be needing this uh, for large area, we will be needing coarse grit. Okay, so for large area, we will coarse grit will be used, and for smaller area, fine grit is to be used. So is it clear to you?
Yes, sir.
Okay, and regarding grade, that was the part I was confused. So yeah, in the first part, so since the pressure P1 is less than P2, right? P1 for large area and P2 is for small area. Now P1 is a higher pressure and P2 is a large P2 is a P1 is a smaller pressure, P2 is a larger pressure. So P1, for withstanding P1, the abrasive should be very strongly attached with the wheel so that they do not move. For withstanding P2, that is a higher value of pressure, the abrasives must be strongly attached with wheel, so hard. And for this one, if even if the abrasives are not very strongly attached, but since the pressure will be less, so even soft grade abrasive can also will also be able to withstand this low pressure. So for large area, soft grade will be used. So is this clear to you?
Yes, sir.
Okay. So to summarize, we can write that large area implies low pressure, implies coarse grade or lesser number of grades, and soft grade. So from this, from these two, we are seeing that for dry grinding and large area, we will be needing soft grade and coarse grade. So the correct option is option number A. Okay. So coming to the next problem, creep grinding involves which of these? This I hope is discussed, so I think so you should be able to answer this. Anybody? What is creep grinding?
So is this related to the creep? I mean the time dependent deformation.
No, 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 not the creep deformation. That is different. This is a type of grinding.
Okay.
So creep grinding is basically one in which in general we use very low depth of cut and high feed in case of normal grinding. But for creep grinding we use a very high value of depth of cut. Okay, something like this.
Sir, option D.
High depth of cut and low feed rate. So the high, there will be high depth of cut and low feed rate. So essentially the material removal rate remains essentially almost similar, but the high depth of cut is accounted for by the low feed rate. So this is the creep grinding. So the correct option is option number D. Okay. So yeah, coming to the next problem, in plunge grinding, which of these is correct? The width of the wheel and the length of the workpiece. So let me give you an idea. Mm, what is the width of the wheel? So supposedly this is the grinding wheel. Okay. So this is the width of the grinding wheel. Okay. And this is the workpiece. This is the length of the workpiece. So uh, can you tell me what will be the relationship between the width of the grinding wheel and the length of the workpiece in case of plunge grinding?
So option B.
Option D, no particular
B. B.
relationship.
B.
Huh?
B.
B,
Option B.
width of the wheel is less than the length of the workpiece.
Yes, sir.
Okay. So see, what happens in plunge grinding is that what happens in grinding is, suppose this is the workpiece and this is the wheel. Okay. So this wheel, this is the width of the wheel. W, and this is the length of the workpiece. So the wheel on rotating, this is being rotated, and the wheel is also fed in this direction. Okay, and the wheel is also fed in this direction. This is called in feed. This is called a traverse, and this is the cutting motion. Okay, the circular motion is the cutting motion. This is what general grinding looks like. But in plunge grinding, as the name suggests, it is directly the plunging of the wheel. Plunging is like a kind of dipping of the wheel. So if this is the workpiece whose length is this, then the grinding wheel will be something like this, rotated in this direction, grinding wheel, and there will only be in feed. Okay, or plunge, you can say plunge. And there is no traverse motion. Okay, so for this to happen, the width of the wheel has to be more than the length of the workpiece. Greater than length of workpiece. So the correct option is option number A. Is it clear to you?
Yes, sir.
Okay. So let's move on to the next problem. So in centerless grinding, the regulating wheel performs which of these functions? So what is in centerless grinding? What is the function of the regulating wheel? Can anybody give an answer to this? Yes, anybody?
Sir, option A.
Performs a machining operation. Okay. So, but what is the difference between a regulating wheel and a grinding wheel then? We could have called it a grinding wheel, right? See, this centered and centerless grinding comes in into picture for cylindrical, for the grinding of cylindrical workpieces. Okay, so for centered grinding, what happens is centered grinding. Say so, the workpiece is held like this, and say this is the tail stock and this is the head stock. The workpiece is rotated or even kept stationary, and the grinding wheel is brought into contact like this. This is the centered grinding, that is the workpiece is centered or fixed to a particular between two particular centers. This is centered grinding. And centerless grinding. So what happens in centerless grinding is, suppose this will be one grinding wheel, this will be one wheel, this is the workpiece, Okay, this is supported on a base blade called the rest blade, and this is another wheel. Okay, so this is called a grinding wheel, and this is a regulating wheel. So there is no necessity to give two cutting wheels, two machining wheels on both the sides, right? So what will be the use of this grinding wheel, regulating wheel? See, this raised blade is so the machining operation is performed by grinding wheel. So suppose the weight of the workpiece. Can anybody tell me by intuition which one will support the weight of the workpiece? Anybody? This is very common, right? Which one is supporting the weight? Where is the weight acting of the workpiece? This is the weight. So which one is supporting it? From this diagram, at least this is clear, right? That the weight is acting in this direction. Then which one will support this weight? Which one of these is supporting the weight?
So that rest plate.
Yes. So the raised blade supports the weight of the workpiece. Helps in rotation. See, the rotation is done by the grinding wheel itself. Okay, or there might be since the grinding wheel is rotating, the workpiece will also rotate along with it. Okay, even if the workpiece is held stationary or workpiece remains stationary, then the relative motion between the grinding wheel and the workpiece will do the cutting operation. So this is not a function of essentially the regulating wheel. What is the function of regulating wheel is, if we see it in from this direction, if we see, okay, if we see, then we will see find that the arrangement looks something like this. This is the grinding wheel. This is the workpiece. Okay, this is the rest plate on this, and the regulating wheel is something like this, which is inclined at an angle to the workpiece. Angle of inclination being I. So when this regulating wheel as the regulating wheel is rotating, okay, it will give a transverse longitudinal feed to this direction, to the workpiece. Gives, see, there is one wheel like this, there the workpiece is attached in this direction, the workpiece is attached in this direction. Now there is another wheel which is like this, which is rotating in this direction. So due to this motion, the workpiece will also have a longitudinal movement like this. That is the function of the regulating wheel. So gives longitudinal movement workpiece. Okay, so is it clear to you?
Yes, sir.
Okay, so the next problem, the honing refers to which of these?
Sir, option D.
Yes, correct. So honing is the process of use of abrasives. Yes, am I audible now?
Yes, sir.
Yeah.
Yes, sir.
So suppose this is an already existing hole, and this is the honing wheel which will be rotated in a direction like this, and on the body of this honing wheel, sorry, sorry, yeah, these are the abrasive sticks attached. They are also called hones. So these are the abrasive sticks. Okay, so the use of abrasive sticks to finish or correct this existing hold is called honing operation. So the correct answer is option number D. Now for lapping operation, the material removal action for soft material is which of these? Embedded abrasives in tool, erosion by abrasives hit by tool, pressure of slurry alone, or high speed rotation of workpiece.
Sir, option D. High speed rotation workpiece.
Mm, See, one high speed rotation is always involved, but is it the only material removal action? That is what the question is. Like high speed rotation is not the uh, mm, phenomenon by which main phenomenon by which the material removal is happening. So what happens in lapping is, suppose this is the workpiece that we are trying to finish, and this will be the tool. So the tool will have a shape which is conformal to the shape of the workpiece. Okay, and in between them there is a slurry. Okay, the slurry will have something like kerosene or oil with abrasives. Now there a pressure will also be applied. So the pressure of slurry alone will not be responsible for the machining operation. The high speed rotation of the workpiece will also be not alone responsible for the removal of the material. So what will happen is that you have to, it is particularly asking for soft materials. So we have to focus on the soft material thing. So what happens for hard material? So hard material, what will happen? Mm, uh, the abrasives will be stricken by tool. That is, a tool will strike this abrasive. Suppose this is a tool, simplified view, and these are the abrasives here on the slurry. So due to the motion of the tool or the motion of the workpiece, that is a relative motion between them. Due to the relative motion between them, the tool will strike these abrasives, and this will move down and strike the workpiece in turn. Okay, so due to the striking of the abrasives, small fractions will be eroded. Erode the workpiece. In case the hard tool material is hard. Now, if the tool material is soft, then these abrasives will be attached. Suppose this, then suppose this is the tool material is soft, then from the slurry the tool material will gradually attach. They will penetrate into the penetrate into the tool and attach themselves with the tool. So the abrasives will be attached, or a better word can be not attached, but better word can be embedded. The abrasives will be embedded into the soft tool. Say for if the tool material is something like lead, okay, and this tool with the embedded abrasives will do the cutting operation, performs cutting. Okay, so for soft materials, for the soft, or rather we can say for soft tool material here, okay, then the cutting action will be by the embedded abrasives in the tool. So for correct option here will be option number A, embedded abrasives. Yeah. So is it clear to everybody?
Yes, sir.
Okay. Now truing. Truing refers to which of these?
So, in that reaming and what is the difference between reaming and honing? Is both same? Is
Which one?
reaming and honing?
We have not discussed about the reaming operation, right?
No, sir.
So is it like essentially a question in your assignment?
No, sir.
Okay, so you just want to know about the reaming operation.
Yes, sir. I think it was finishing inside the hole, or uh, is there no relation between them?
See,
Both of them are
reaming
continuous.
operation is related to the machining, like it is not for a finishing operation, but honing is essentially a finishing operation, right? The material removal will be less. So for reaming, the cutting edges and the material removal will be larger in compared to the as compared to the honing operation. That it won't be using abrasives essentially. Okay, so it will be a cutting tool. The surface roughness can be reduced, but it is not essentially a finishing operation, or the surface roughness will be not be as low as we will be getting with a honing operation. Okay.
Okay, sir.
Yeah. So you can say that reaming is used for improving the accuracy. So supposedly a hole is not accurately built or accurately drilled, so we can improve the accuracy of the hole using a rimming operation. But the honing operation is used for the finishing of the hole. Okay, like surface finishing or giving a final touch to the hole.
By meaning the boring means we will be increasing the dia of an existing hole, and by honing, it will be actually finishing, and by reaming it, we will be refining their tolerance.
See, boring refers to if we increase the diameter of a hole to a certain extent. Supposedly, this is the hole, and yeah, we are increasing the diameter of the hole. Suppose we are increasing the diameter of the hole, okay, like this. Then this is the boring operation, okay. But if we are suppose this is this has very high roughness here and there, so or the hole is not built properly, say there are it might be tapered or something like that. Suppose there is a taper like this or something like this, then we can remove those by rimming operation. And honing is particularly used for the finishing of the hole, that is the surface roughness is to be decreased.
Okay, sir.
Now truing, so what does truing refer to? See, when we are mm, when the grinding wheel is machining a workpiece, the chips have the tendency to get attached in the space between the abrasives. Also, the abrasives have the tendency to become blunt. Now, once the grinding wheel loses its sharpness or it becomes clogged by the grinding wheel, sorry, by the chips, we use the dressing operation. Okay, dressing operation to uh, mm, remove these chips or remove the worn out abrasives. So the use of this star shaped tool to remove the clogged material is called dressing. Okay, or the removal of worn out abrasives is also partly done. Now, during this dressing operation, suppose this is the grinding wheel and we are using a diamond shaped tool or star shaped tool, okay, or another grinding wheel. Say you are using another grinding wheel also can be used, okay. But if this grinding wheel is not properly aligned or properly positioned with the existing grinding wheel, or the material is not uniformly clogged throughout the periphery of the grinding wheel, then this grinding wheel will become uneven, okay. Uh, there will be like unevenness or something like this, okay, that it won't be perfectly circular, okay. Now to restore the perfectly circular shape of the grinding wheel, we will have to use another wheel called the correcting wheel. To restore the circular shape of the wheel, because if the grinding wheel is not circular or if it has lost its circular shape, okay, in that case mm, the the grinding operation will not be as far as our requirement, okay. At some portion it will remove greater material, at some portion it will remove less material. So to restore the circular shape of the grinding wheel, okay, we use this correcting wheel so that a perfectly circular shape is produced, and this process is called the truing operation, okay. So the truing refers to the use of the correcting grinding wheel to restore the circular shape of the wheel. And what does the drilling of weights on the grinding wheel is referred to? This is called balancing itself. This is the balancing operation. Suppose the wheels are such that because of the non-homogeneous distribution of the abrasives, one region, suppose this region is more heavier. So when this region will go on a side, this will have the tendency to produce a torque or a couple, okay, on the entire grinding wheel. But we don't want that. So counter weights will be put or placed at locations opposite to the heavier sections. Counterweights will be placed. Counterweights drilled into the grinding wheels. Okay, so this is referred to as balancing. Okay, so the truing refers to this restoring of the circular shape. Balancing is the drilling of weights on the grinding wheel for balancing uneven weights, and dressing is the use of star-shaped tools to remove the clogged material. Okay, so is it clear to everybody?
Yes, sir.
If there is any doubt in any operation, you can ask. Let's see. Okay, now, uh,
So,
yes.
uh, uh, for finishing of the counters and screws, I mean, we need to, we'll be making a counter for fit the counters and screw, isn't it? So, what operation will be used for that finishing of that counters and part?
Sorry, I
We,
didn't get you. Can you please repeat?
I mean, which operation will be used for finishing the counters and region of a for a screw. I mean, we will be, in order to insert the countersunk screw, we will be taking a counter for the surface, isn't it? So it will be actually a hole with a tapered position. So can you use that honing for the finishing of that tapered
You are
section?
saying for finishing of sections like this, the screws, these sections.
Note the this section. I mean, there is a countersunk portion at the top. There will be a tapered head for the screw, so that it will be sung inside the uh,
This section you are saying.
I mean the head of the screw. It's actually thread, isn't it?
Yeah.
If we consider the thread of the screw, head of the screw, it will be for the countersunk screw. It will be a tapered head.
Okay. I'm
So
not
actually,
exactly certain what exactly you were saying for this. Okay. You were saying okay the head of the screw. Okay, I got it. Yeah. So mm, you were saying the which kind of screw you were referring to?
countersunk screw. It will be actually when we screw it to the material, we want the head of the screw will be get inside the surface of that material.
Yeah, yeah, yeah. I got it. Okay, I got it now. Yeah, I got it now. Okay, so you were saying, so you were referring to the flat surface or the threads? That's what I'm saying.
The flat tapered surface of the screw.
So
Actually,
see, for the tapered section, if you are making a tapered section and you are trying to finish it, uh, mm, if you use the honing operation, then what I can say, the honing operation, I don't think the honing operation will be the better option. The lapping operation can be used because then you can make the tool in form of the tapered profile, and then you can use this slurry technique or the lapping method for finishing that. Okay, I am not 100% certain how these countersunk screws are finished, but these threads are not finished by honing. But mm, uh, for the countersunk head part, the flat part, I think the lapping, if they are tapered, then lapping will be a better option, because if you use the honing, then the surface will become regular, or a flat surface it will result.
Okay, sir. So for the tapered hole, I mean the fit of that head, isn't it? There will be a head tapered hole for that fitting of that screw, isn't it? So if the hole is tapered, we will be using the any different method for surface finish of that portion.
See, that is what I am saying, that the tapered hole of the tapered hole of countersunk screws, if you are to keep the tapered shape, then you have to essentially use a tool of this form, like lapping operation, where the tool will be in the form, a counter form of the tapered region. But this cannot be achieved in
Okay, sir.
honing operation. In honing, if you use a honing operation for that tapered section, it will gradually become a regular flat surface.
Okay, sir. So this will be the same for that threaded part also.
No, 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 no. For the thread section, we generally use electroplating methods, yeah, or like electroplating methods, or electrical methods. What I can say, yeah, electroplating methods are generally used for the finishing of the thread section. Okay,
Okay, sir.
okay. So, like in electroplating method, what will happen is that. Uh, uh, like there will be you know uh, what I can say, there will be an electrolyte and stuff like that, so the regions where there will be protruded sections, they will be moved, they will result in a lower voltage, so the material will start getting removed from those sections first. So that is how the threads are usually finished, the threaded sections.
Okay, sir.
Okay. Yeah, because otherwise for honing, for any kind of, if you, even if you are making a formed tool, it will be very complicated. It will be very complicated for every kind of thread that you make, for every configuration of the thread that you make. So that is not a other than the standard ones. For any other thread that you make, it will be very difficult to make another form tool for that itself. So that is why these electroplating methods are used for finishing of these screwed areas.
Okay, sir. So if we need to finish surface finish a large material like turbine blades and everything,
Hmm.
so if we use the grinder wheels, the design will be altered, isn't it? I mean, the if we use the grinding wheel compared to the turbine blade, it will be very small, and if we are doing it in different places, different direction, then the dynamics will be. I mean, the surface finish will be irregular, isn't it? So such a kind of larger materials, I mean, which are casted, how we will be which
See,
material?
they are generally, you know, what I can say, very high accuracy, s- uh, like robotic finishing techniques are usually used for turbine base. It is not just, you cannot just say that the general mm, honing or grinding will be used. Okay, so what I can say that mm, there are many other methods, many non-conventional methods for finishing and polishing. Okay, like electrochemical polishing is there. Okay, laser-based polishing is there. So there are a lot many techniques for polishing, uh, which essentially very fine abrasives with the use of robotic technology can also be used, so that whatever you are saying, that it will not be uniform and all, so those all have to be controlled using a computer or using a program, so that those difficulties do not come. You cannot just finish a turbine blade using your hand. There are specified machines designed for that purpose. And yes, abrasives can also be used, very fine abrasives, diamond based abrasives can also be used for the finishing of those turbine blades. But essentially the movement has to be controlled very precisely, say using the use of computerized robotic arms. Okay.
Okay, sir.
So should we move to the next problem?
Yes, sir.
Okay. So a grinding ratio of 400 implies which of these? So grinding ratio is 400, right? So which one will be the correct answer? Yes. Anybody? This is very simple one, right? So grinding wheel wear will be what? Grinding wheel wear is MRR by 400. That is 0.0025 times the material removal rate. So the correct option is option number B. Okay. So is it clear to everybody?
Yes, sir.
Okay. Now the heat dissipation involved in arc welding with direct current is which one of these? So we are now moving to the joining process. The questions related to joining operation. That is essentially we will begin with the welding operation. So the heat dissipation involved in arc welding with the direct current is which of these?
So it will be like positive section will be more, 70% will be removed, will be taking
70% will be in what?
positive section.
In
I
which
mean,
section?
the connected to the positive.
So what is that? Is it cathode or the anode?
I think it's anode. So it's anode.
Yeah, just a minute. So the positive, the one that is attached to the positive terminal is called the anode, and the one that is connected to the negative terminal is called the cathode. Now tell me which one will have the higher heat? That is, where will be the greater heat generated?
So anode, since electrons will be flowing to the negative to positive.
Yes, correct. So suppose this is the anode, or suppose, yeah, so this is the anode. Suppose this is the electrode here, and this is the cathode or the negative terminal, or is here. Then the electrons will flow from the cathode to the anode. So when the electrons strike this anode surface, their kinetic energy will get converted to the thermal energy, which will be, you know, which will come in the form of heat. So two-third of the heat will be generated. Two-third heat is generated at anode, and one-third heat is generated at cathode. Okay, so the correct answer is option number B.
So, is the material that electrode that connected to the positive always anode? I mean,
No, no,
there
no,
are
no, 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 definitely no. So this is if the electrode is connected to the positive terminal, then it is called the direct current reverse polarity. Okay, and if the electrode is connected to the negative terminal, so if the electrode is positive and the workpiece is negative, okay, then this is called a direct current reverse polarity. Okay, direct current but reverse polarity because we actually want that the electron should strike the workpiece if we want the material to be removed from the workpiece more. We don't want the workpiece to be having less heat, then less heat will imply that the material will be removed less from the workpiece. And direct current straight polarity will mean that the electrode is negative and the workpiece is positive. Okay, so this is direct current straight polarity.
so actually what I was asked is when during the electroplating actually electrode that is connected to the positive will be considered as a anode and the
Yeah,
other one
yeah,
will be cathode. But in the electrochemical cell we will
yeah,
be
yeah, yeah, yeah.
reversing it.
Electrochemical cell. It depends on the oxidation or the reduction reaction that happens in the cell. So that is different. That is different. Okay. So uh, you know, it depends on if we are losing the electron at the cathode or the anode. In that case, for electrochemical reaction, here the electron is directly moving from the negative terminal to the positive terminal. So the negative terminal is called the cathode and the positive terminal is called the anode. In electrochemical reaction, it will be opposite because essentially the release of the electrons at different at the places will be different. At the anode, that is a particular electrochemical reaction resulting in the release of electron and the absorption of electron will be different. That is why they will be positive, that is the anode will be negative and the cathode will be positive. Okay.
Okay, sir. So if we are connecting to a battery or power source like this, we don't need to be confused with this thing. Only the electrochemical reaction like that we need to be careful about.
Yeah, in electrochemical reaction, the you have to go through the reaction specifically to understand like where exactly the electrons are getting released and where the electrons are getting absorbed. So where the electrons will be released, the change in the oxidation and the reduction, and that is the change in the oxidation number. And where the electrons are being absorbed, then the change in the oxidation number. So depending on that, the electrons have been identified as anode and cathode in case of electrochemical reaction. But in case of electroplating or electrolytic reaction or this whatever we are using in case of arc welding, the cathode where is one where the electrons will be released, and the anode will be the one where the electrons will be absorbed. Okay.
Okay, sir.
Yeah. So going to the next problem. So the resistance welding basically depends upon which of these?
Sir, ohmic resistance.
Yes, ohmic resistance. Now, the inability of the weld metal to reach the weld joint, root of the weld joint leads to which of these?
Incomplete penetration.
Yes, complete penetration. Now, vacuum is required for a high precision weld joint in case of which of these?
Electron beam.
Yeah, electron beam welding. Why is high vacuum required?
Sir, the oxidation or
See, that is why you should know the basic before like you know memorizing or going just by the facts. What happens in electron beam is that a beam of electrons like this, it is directed to a workpiece. Okay, the kinetic energy of these electrons is what gets converted to the thermal energy and results in the melting. So if there is some pressure here, particular pressure here, then the movement of the electrons will get diverted like this. So there will be a loss of the kinetic energy. If there is vacuum, then the electrons can strike the material directly. That is why a high vacuum is required in electron beam welding, for so that the electrons without getting diverted can strike the workpiece material directly. Okay, so that is why a high vacuum is required.
Okay, sir.
So yeah, and large heat effective zone in arc welding process happens during which of these? Large heat effective zone.
So power density more.
Are you sure this is the correct option? Because power density means or energy supplied per unit volume. So for high power density, the volume can also be very small, so that the power density is high. And if the volume is very small, then the heat affected zone will also be less. Okay,
So V is the volume of weld or volume of the material.
sorry.
So V is actually volume of weld or volume of the material workpiece.
Welding of material or welding of workpiece is same. It's not it.
Uh,
Welding, the our basic aim
I
is to
mean the
weld the workpiece.
weld area. The we'll be welding some areas in it. So
Yeah.
V is actually the weld bead. There is a weld bead volume, isn't it?
See, the what happen weld bit is something, it is formed when, suppose this is the material being deposited. When an extra material is being deposited, this is the weld bit. This is the section that has melted and solidified. Okay, and this will be a heat affected zone where the heat could change the structure of the grains here. Okay, this is the heat affected zone. Okay, now if the power density is high, that means for this same value of E, even if the volume at which this is coming, this area is very less, if this area is very less, then also the power density will be very high. Like laser beam welding, electron beam welding, the power density is very high because the area or the volume that which it is interacting is very less. In that case, the power density will be high, but the heat affected zone will be very less. But if we are using a very high heat input refers to this energy input. Okay, if the heat input basically is very high, then whatever area you use, small area or large area, irrespective of the area, the heat affected zone, this heat will impact a larger area, so the heat affected zone will be more. So the welding with high heat input results in a large heat affected zone.
Okay, sir.
Yeah. So the correct option is
So for the direct polar, I mean, if we are connecting the workpiece to the positive, then we'll be having more penetration, so the heat affected zone will be also more.
which one?
I mean, if we are connecting the workpiece to the positive side, then the penetration will be more, isn't it? So the heat affected zone will be also
Yes, 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 obviously the
okay.
heat affected zone will be more. Yeah. So for direct current straight polarity, the workpiece, more heat will be generated at the workpiece, that is the cathode section, and sorry, more heat will be generated at the workpiece, which will then be the anode of the setup, and in that case, the heat affected zone will also be more. Yeah. Okay, so uh, let us end for today. We will discuss more questions related to the joining and welding process in the next class, and mm, then we will move on to the surface treatment processes. Okay, so thanks for joining, and please join the next class.
Thank you, sir.